Hello everyone and welcome to Mathematics and Dynamics lectures. In this lecture I will explain how to represent vector cross product as matrix vector multiplication. Before I start with explanations, I would like to give a few important comments. In these lectures we present real and applicable knowledge that will help you to become a successful mechanical, aerospace or electrical engineer. Secondly, it took me a significant amount of time, energy, and planning to create this completely free video tutorial, as well as 300 video tutorials that you can find on my YouTube page. And consequently, I kindly ask you to press the like and subscribe buttons. Thank you very much. Okay, let's start. First, let us talk about motivation for representing vector cross product as matrix vector multiplication. For example, if you deeply study dynamics or if you study dynamics of rigid bodies, you have probably seen these type of expressions. This is a triple vector cross product. And let us imagine that you want to write a Python code that will perform some multiplication or that will use this expression. How would you do that? Well, of course, you can compute this expression a priori and then you can code it. However, when we perform multiplications or computations in Python, C++, C, or MATLAB, we like to use matrices and we like to use vectors. And consequently, it's very important to learn how to represent a vector cross product as a product of some matrix and some vector. This tutorial will teach you how to do that. First, let us briefly revise the vector cross product. Let A be a three-dimensional vector with the components ax, ay, and az. And similarly, let B be a three-dimensional vector with the components bx, by, and bz. Then, the cross product, or I like to call it as a vector cross product, is defined by this expression. A cross B is equal to formal determinant of I, j, k, where I, j, and k are the unit vectors of x, y, and z axes. Then we have ax, ay, az, and then we have bx, by, and bz. Let's compute this determinant. We obviously have I vector multiplying ay, bz, minus az, by. Then we have minus j, unit vector, multiplying, let's see what do we have, ax, bz, minus az, bx. And we have plus k unit vector, multiplying what? ax, by, minus ay, bx. This expression can be expressed as the following vector. A cross B is equal to. Over here we will put x components, and the x components are ay times bz minus az, by. How about the y component? Here's the y component. And I will multiply this expression by minus 1. As the result, I have az, bx minus ax, bz. Then, the z component is this component, ax, by minus ay, bx. Over here, I rewrote this expression twice, and let's see why I did that. Well, here's the main goal. want to represent this vector product as matrix vector multiplication, where over here I will have the vector A with its components AX, AY, and AZ, and over here I want to have a matrix B that depends only on the components of the vector B. I will represent this matrix as B as a function of B. On the other hand, over here I would like to have a vector B with its components Bx, By, and Bz multiplying a matrix that depends only on the components of the vector A. I call this matrix capital A of A. And we need to determine the structure of this matrix and the structure of this matrix. Let's see how to determine the structures of these matrices. Let's start with the first scenario. What happens over here? I have AY multiplying BZ. Consequently, I need to have BZ over here. Next, let's see what happens over here. I have BY multiplying AZ. This means that over here I need to have minus BY. Perfect. What happens over here? I need to have 0. Let's verify this expression. 0 times AX is 0. BZ multiplying AY gives this term over here. Then I have minus BY multiplying AZ, and that's precisely the term over here. Let's continue with the second row. I have BX multiplying AZ, and consequently the third element on the second row should be BX. How about this term over here? I have BZ multiplying AX. Consequently, I have minus BZ. And over here, I need to have 0. Let's verify this expression. Minus BZ times AX is precisely the term over here. Then 0 times the AY, I don't have AY over here, and BX times AZ, it's precisely the term over here. Let's apply the same principle to the third row. Let's see what do we have. I have AX and I have BY. Consequently, I need to have BY over here. Then I have AY, okay, and need to add minus BX. So here is BX, and here is 0. Let's verify this. I have BY times AX, that's the term. Then I have minus BX times AY, that's the term over here. Perfect. Let's apply the same principle to the second case. Over here we want to place the projections of the vector A. And let's see how to do that. First we need to notice that I have BZ over here. Consequently, I need to put AY over here. Then I have minus AZ times BY. Consequently, I need to have minus AZ over here. And I have 0 over here. Let's continue. How about here? I have BX. Consequently, I need to have AZ over here. And I have minus AX times BZ. Consequently, I need to place over here minus AX. And I have 0 over here. How about the third row? I have BY times AX, and I need AX over here. And what happens next? I have BX multiplying minus AY, and I need AY over here. And that's it. Congratulations! We are able to represent the vector cross product as vector matrix multiplication, and we have two forms. Next, I need to give a few important comments. Let's see what happens when we transpose this matrix. That is, let's try to compute B transpose. And to do that, I will simply erase this part, since I will need as much as possible of my screen, and I will do this. Okay, this matrix is B matrix, and this matrix is A matrix. Let's see what is B transpose. B transpose is, we take the first row and we write it as the first column. Consequently, we have 0, BZ minus BY. Then we take the second row and we write it as the second column. We have minus BZ, 0, and we have BX. What happens over here? We take the third row and we represent it as a third column. And we have BY minus BX, and we have 0 over here. Let's see what this product, or actually this transpose, produced. Below, let's write our original B matrix. So this is our B matrix, and let's write it 0 BZ minus BY minus BZ, 0 BX BY minus BX, 0. And let's compare these two matrices. What do we see over here? We can observe that B transpose is simply minus B. This is a very important observation. Similarly, you can show that A transpose is minus A. Matrices that satisfy this property are called skew symmetric matrices. That is, to transpose this matrix, we take that matrix and we just add minus, and that's it. Now, let's go back to the beginning of this video and let's consider again our motivational example. We wanted to compute something like this, and we want to represent this triple cross product as a vector matrix multiplication. Let's apply everything what we learned in this video tutorial to this case. First of all, let's write A as AX, AY, AZ, B is BX, BY, BZ, and C is CX, CY, and CZ. We can represent this triple cross product as the product of the matrix A that depends only on A and this vector over here. However, this vector over here can be decomposed as the product of a matrix that depends only on the components of B and the vector C. Let's do that. Over here, I need to enter CX, CY, and CZ. Over here, I need to use the formula that we previously derived. Consequently, I will have 0 minus BZ, BY. In the second row, I will have BZ, 0 minus BX. Then I will have minus BY, BX, and 0. What happens over here? I need to apply the same formula. I will have 0 minus AZ, AY, then I will have AZ, 0, AX, no, here I have minus AX, be careful not to make a mistake, then I will have minus AY, AX, and I will have 0. Let's verify. 0 minus AZ, AY, AZ, 0 minus AX, minus AY, AX, 0. And that's it. Consequently, we were able to represent this triple product as A times B times the vector C. And that's it. You can easily code this in Python, C, C++, or MATLAB. Okay, that would be all for today. I hope that you liked this video. If you like the videos I create, please press the like and subscribe buttons. Thank you very much.